We're going to jump right into 10.2. So 10.2 is still working with rational expressions. And specifically adding them and subtracting them. Okay. Now, just as a reminder from what 10.1, 10.1 was rational functions. 10.1 is rational functions to start with, so we've got a function defined by some rational expression. There's an algebraic way to write a rational function. It is a function, and it is defined by or described by a rational expression as opposed to a linear expression or a quadratic expression. This one's defined by a rational expression, and a rational expression is just a polynomial on top of a polynomial. And for rational functions, we could evaluate them. There we go. If you know x, you can plug in x and solve for the value of the function. Or if you know the value of the function, you can solve for the value of x. Whether you're doing this because you said, here's f of x equals this, find x equals 3, for example. Or if you have a word problem where you have to plug in something you know and it spits out the other thing you don't know. And you have to say, hey, here are my two variables, my x and my f of x. Which one do I know? Which one's missing? Plug it into the right place and find the missing thing. So evaluating and also finding the domains. How is this restricted? How is a rational function is restricted if anything makes the denominator undefined? So you find what x cannot be, and once you know what x can't be, you know its restrictions, you can write what it can be, its domain. X such that x is a real number and x is not equal to -2, for example. And we also looked at then, putting the functions aside for a second, we just looked in closer at those rational expressions. A rational expression is that capital P over capital Q, a polynomial over another polynomial. And specifically, we looked at simplifying them, multiplying them, and dividing them. Simplify, multiply, or divide. We're not solving anything here. There's nothing to plug in or evaluate. We're just taking that polynomial over the other polynomial, and we're putting it in lowest terms, just like putting a fraction in lowest terms. And of course, in order to do so, in order to simplify, multiply, and divide, we have to, of course, first factor completely, because you can only cancel out factors, not terms. And once it's factored completely, then you can cancel out factors of 1. Anything that matches equals 1. And so you can cancel it out because times 1 doesn't change anything. Or if you see opposites, which is just two subtractions, but in opposite order, both of them subtraction, but one like x minus 4 or 4 minus x. So that's a factor of -1. And you can cancel out opposites as well as long as you throw a negative out front. It's like GCFing out a -1 and putting it out front. Our basic setup for simplifying, multiplying, and dividing is just like fraction. I'll just use simples A, B, C's, and D's. And these can stand for regular old numerical fractions like 3/5 or 1/2. Or it can stand for more complicated rational expressions, a polynomial over a polynomial. The mathematical rule, the mathematical law is the same. If you have some fraction, be it a polynomial over a polynomial or just a simple fraction, and you multiply it times another fraction, all you are doing is multiplying straight across. You do not need a common denominator. Okay? And so that leads to A times C on top and B times D on the bottom. And of course, if you can put it in lowest terms, you do. If there's anything you can cancel out, any factors of 1 you can cancel out. For example, if you ended up with just fraction multiplication, you end up with 6 over 10, you would reduce that to 3 over 5. because you could cancel out a factor of 2 on the top and the bottom, like dividing by 2, top and bottom, as long as you're fair. Now with division, you have some fraction or rational expression divided by another one. First, you change that to in terms of multiplication. A over b times all division is multiplying by a reciprocal. Okay? So you flip it, and then you can multiply straight across. So here we have AD over BC. And of course, if there's anything that can be canceled out or reduced to lowest terms, you do so. But the key is, you do not need common denominators when you are multiplying fractions, and that same rule applies to when you are multiplying or dividing rational expressions. They're more complicated with polynomials instead of plain numbers. You do not need common denominators. Okay. Now that was our focus on Thursday. Okay. Our focus now in 10.2, as I said, is to add and subtract. Rather than multiply and divide, where we do not need common denominators, we're going to be adding and subtracting rational functions. I'm going to abbreviate there. Rational expressions. And we absolutely do need common denominators. So if you just think of your rule when you are like I said, that's all from 10.1. And now 10.2, we're adding and subtracting where we do need common denominators. And just think of adding or subtracting a simple fraction. That's all a rational expression is just kind of an ugly fraction. Lots of variables and stuff involved in it. But you have some fraction, let's say a over b, or rational expression, and you're adding it to, let's say, c over b. Do you have common denominators in that case?
Yes.
Yeah, our common denominator is b. So when we simplify this,
AC over B.
not ac, what is our common denominator?
B.
Right, it's not b squared, it's not 2b, okay? Think of this as like if you have a pizza cut into 8 slices. Huh? Well, let's hope they're all cut the same size, because if they're all cut in different sizes, you might have one slice and I have one slice, but mine's really tiny and yours is really big. That's not really fair. Just because we each have one doesn't make it fair. Right? Our pizza has to be cut into 8 equal slices. That's what a common denominator means. It means all of the pieces are the same size. Therefore, it is fair. So if I eat one slice of an 8-slice pizza, and you eat one slice of an 8-slice pizza, or let's say I eat one slice and you eat 2 slices, how many slices were eaten? 3. So you add or subtract, depending, the numerators, 1 plus 2. Huh? But the pizza is still cut into 8 equal slices. The denominator stays the same. Now, if you're comfortable with that principle, basic fraction addition and common denominators, I just want you to keep in mind, as we get more and more complex looking with rational expressions with polynomials, it's still following that same mathematical rule. When you add or subtract fractions, whether they're simple rational numbers or rational expressions with polynomials, you need a common denominator, and that denominator doesn't change. That denominator is the size of your pieces, and that stays the same. You're not doubling it, you're not squaring it, it is b. Once you have them both b, it is b. And you're just adding or subtracting. Then you must combine your numerators and simplify them. And then, at the end, you simplify to lowest terms if possible. So everything we did last week was simplifying. Once we add or subtract fractions, we may have to put them in lowest terms, which is what we did here. Simplify. We make sure everything is factored completely and cancel out any factors of 1. So in the end, after adding or subtracting, we still need, our last step is to simplify if possible. Just like changing 6/10 to 3/5. Okay. Now, our basic job here, I'm going to put the 2 sort of basic first steps, but then we're going to start working through them and see really what they mean. We need common denominators. Okay. The definition of an LCD, so the least common denominator. So our least common denominator, this is its definition. It is the product of the unique factors in the denominators. So however many denominators you have, 2 or 3, whatever many things you're adding or subtracting, you look at those denominators, and the LCD is the product, meaning multiply, of all the unique factors. So every unique factor you see in the denominator of the things you're combining is one of the factors that's in the LCD. And so in order to make this happen, first you must factor all denominators completely, because you cannot have a product of those factors until they are factored. Factor all denominators completely. Now this is what you must do if you don't already have common denominators. First we're going to look at cases where we have common denominators, and then move from there. And if we don't have common denominators, we're going to need to find the common denominator and change everything to have the common denominator. Once we have that, we will just combine and simplify our numerators. Now, I'll warn you right now, as we move forward, this is some of the messiest work you'll do in 310. Okay? It can be intimidating looking because it gets very messy. It can fill up your paper. Okay? It can get very chaotic. And that's what makes it look intimidating. I'm going to be showing and modeling some steps to keep things as efficient and organized as possible. Okay? Not because I'm that OCD, which sometimes I am, but the point is that the messier and more chaotic things get, the more the more your brain gets frustrated, and the more easy it is to make careless mistakes. Okay? So you may find as you practice your homework strategies, organizational strategies and all that work for you. And I'm not judging you on your organizational strategy. I'm not grading you on that. But I'm going to show you some things that I find work for me and for a lot of students in general. And the point is to be as efficient and clean as possible. Again, not because I'm being all OCD about having a clean paper. It's because when your paper starts to get chaotic, it throws everything off. Careless mistakes, you lose track of where you are. Okay? And this can get very messy, I'm telling you up front, so we want to find ways. Learning how to do this is also very much about how do I stay organized and keep track of my work. You don't want to lose track of where you are, it's all over them. Okay. So, let's look at 3 problems here to start with. Let's do 3 over x times 8 over x, 3 over x divided by 8 over x, and 3 over x plus 8 over x. All right. When you have a rational, you're having to combine a couple of rational expressions, whether they're simple fractions or more complicated. These aren't simple fractions because they have variables. They're not particularly complicated because they don't have big polynomials you have to lock up and stuff. Okay? But either way, they are rational expressions. And your first job is to say, what is my operation? What's the operation here? Multiplication. Does that require common denominators? No. Do you have them?
Yes.
But it doesn't matter. You may or may not. Doesn't matter. You don't need them, so it doesn't. Either way, it doesn't matter. It doesn't affect how you do the problem. It's multiplication, so you are going to be factoring completely, multiplying straight across, canceling out anything that matches. Okay? So is there anything to factor?
3 times 8.
That's multiplying, yeah. But 3x, 8, and x, they're all, yeah. There's nothing to factor, no work to be done. Everything is linear, no GCFs, everything is linear, everything is just a single thing. So, boom, you're multiplied. Is there anything you can cancel out? Anything that matches, one thing on top matches something on the bottom? No. So all you can do is combine. You're combining with multiplication. So, on top we have 24, and on bottom we have, right, it's x times x, which is x squared. So 24 over x squared. And double check, is there anything that can be reduced to lower terms? No, so you're done. Okay. What's my operation here? Right. So we got division. Common denominators required? Nope. Just like this. But we do have to flip. Because multiplication is defined in terms of division is defined in terms of multiplication. All division means is multiplying by the reciprocal. Now, it doesn't matter whether you flip first or factor first, except that I always encourage you to flip then factor, because I find that students who factor first then forget to flip. Or they factor and they start canceling things out, which is illegal until you flipped. So get in the rhythm of flip then factor. Flip first, now see what you have. Now you have a multiplication problem, now you do what you're supposed to do. And is there anything to factor? No. So it's multiplication, everything is factored. Boom, you're multiplied. Now can you cancel out anything?
Yes.
Cancel out those x's. Yeah, one on top, one on the bottom. It's not 24. We still have, keep it in terms of a rational, go across the top, what do you have?
3 over 8.
Over 8. You can't, if something's on top, it stays on top. If something's on the bottom, it stays on the bottom. Changing its place changes its value. Okay? So that's it. It's in lowest terms, so you're good. Here, what is my operation? Addition. Are common denominators required?
Yes.
Yes. Do you have them?
Yes.
So you're good to go. Not a lot of work in this one. You already have common denominators. What's my new denominator? My new denominator.
X squared.
X. Right. Just X.
Why not squared?
Because the pizza has 8 equal slices. The pizza has, the X is the size of the slices of the pizza. That size does not change.
But when you did the multiplication, okay, that's just a rule.
Yeah. Like if you were adding, for example, 1/5 plus 3/5. Okay? A 5-slice pizza. One person eats 1 slice, another person eats 3 slices. How many slices were eaten? But the pizza still had 5 equal slices. That didn't change. It didn't all of a sudden become a 10-slice pizza or a 25-slice pizza. Not magic pizza. That'd be great, yeah. More slices, but they become much smaller. No, it's just, if your denominator, once you have your common denominator, that is your denominator. All you are doing is combining your numerators. Now, I'll point this out here, and it's going to come up again. What is this operation?
Addition.
This is not 3 times 8. It is 3 plus 8. Okay. Giving us, yes. And now before you move on, once you've combined it over one rational bar, basically you took 2 rationals, and with a common denominator, combine the numerators, and so now you have a single rational bar, a single rational expression. Before you walk away, make sure it's in lowest terms. If there's anything you need to factor, factor it, cancel out factors of 1 before you move on. This one, there's nothing to cancel, you're good. Okay. So let's start using more complex ones. But those basic rules, those basic mathematical laws apply whether we're dealing with very simple terms here or whether we are bumping it up to really ugly polynomials. Okay? It's all going to follow the same rules. So let's take x squared over x plus 3 minus 9 over x plus 3. Got two rationals, and what is the operation being performed? Are common denominators required?
Yes.
That's your question. What's my operation? Oh, plus or minus? I need common denominators. Multiply or divide? No, I don't. I just need to factor, flip first if it's division, factor and cancel. No, I need common denominators. Do I have them?
Yes.
Yes. Now, as a rule, go ahead and lock things up. Okay. If you have a common denominator already, go ahead and lock it up. If it's not factored yet, if it's common, you don't need to factor it right now. You will need to factor at the end, but for right now, if it's already common, just lock it up and it's done. Okay? Now, if you can factor the numerators, don't either. Okay? And this is going to come up again as we move. Don't waste your time factoring numerators at the beginning. You will have to factor at the end, but you don't know what you're factoring until you've combined numerators, because combining numerators is going to change the numbers, right? Just it changed 3 and 8 into 11. Okay? So you don't want to do any factoring if possible. It wasn't possible here, but you wouldn't want to do it here because factoring creates parentheses. And since you're going to be combining things, you have to kill parentheses before you combine them. So why do all the work factoring if you just have to kill the factoring in order to combine? Okay? Leave the numerators alone. Okay? Now, if they already do have parentheses, you need to actually unfactor it because you are going to have to combine them, but you'll see that step will come more naturally. Right now, ignore the numerators. Check out your denominators. Your denominators match, so just lock them up. What's my new denominator?
X plus 3.
And what's my new numerator?
X squared minus 9.
Right. X squared minus 9. Now, before I walk away, I need to make sure I'm in lowest terms. Now, if you've got, and this is what your brain should be clicking on. Oh, wait, this isn't linear. Huh? Yeah, it's not linear. If you've got exponents, now it also is a case there may be GCF. So you got to check for GCF, but definitely a brain clue that should, even before checking for GCF, is like, oh wait, that's not linear. If you've still got exponents, you may be, now maybe prime, you may have to walk away, but you need to check. If it's not linear, it's very likely you'll need to factor it, and so you need to do so. And so what do you have here? Is there GCF?
No.
So what do you have?
X squared minus 9.
Difference of squares, which gives you x plus. Right, your conjugates. Good. So that factors into conjugates over your common denominator, which is still common. I just brought it along with me. Okay. But because before I could walk away, I had to make sure everything was fully factored, and so that I could see if there were any factors of 1 I can cancel out, and are there?
Yes. X plus 3.
Now, this is a rational. I'm going to keep it as a rational. What's left on top is x minus 3, and what's left on bottom, if there's nothing left on bottom, what do we put?
1.
A 1. Now, if there's a 1 on the bottom, at this point I can drop it. The reason I'm very consistent about writing that 1, at least until I'm finally done, is so that I don't accidentally put x minus 3 on the bottom. You know, you want to keep it as a rational. As long as it's a rational, if everything cancels out, put a 1, so you keep it as a rational, so you don't accidentally move something down or up that shouldn't be. Now I can say, oh, I don't need a 1 on the bottom, I drop it, and I'm good to go. If the 1 was on top, you can't drop that or move it. So you keep it as a rational. If anything is all gone, put a 1, and then decide, do I need to keep that 1 or can I drop it? Okay? All right, so 8x minus 5 over x squared plus 6x plus 8 plus 7 minus 7x over x squared plus 6x plus 8. You're adding rational expressions. So you see rational expressions and you know, oh, I am adding.
So you have common denominators, so we're fine
Yeah,
with it.
right. Yes, you need common denominators because you're adding, and you indeed have common denominators, so you're good. Now, do you think you'll need to factor these denominators?
Denominators, no.
Well, you will,
At the end.
but just do it at the end, yeah. It doesn't hurt if you do it now. It just is a little cleaner to do it at the end. But there's nothing wrong with doing it now. But if you have common ones, I would just go ahead and move along. Yeah, you can go ahead and lock them up just to be consistent. When I say lock things up, it's better to sort of over parentheses than under parentheses so you remember what things go together. Go ahead and write your common denominator because it doesn't change. Now, it is important definitely to lock up those numerators. Now, before I combine them, should I go ahead and, look, I can factor that, right? Should I go ahead and factor it? Should I pull out that 7 GCF? No. Because I'm about to combine these. I'm about to do 8x minus 5 plus 7 minus 7x. If I factor this, when you combine like terms, first you have to kill parentheses. You have to distribute. So if I factor this, I'm creating new parentheses that I'm just going to have to kill in the next step. I just made more work for myself. Okay? You don't want to factor that numerator until the numerator, you don't, right now you don't know what numbers are in your numerator because you're going to be adding this plus this. So you don't know what numbers the numerator contains. You don't want to factor until you have your numerator. You don't have your numerator yet. Okay? Leave it unfactored, but do make sure things are locked up. 8x minus 5 plus 7 minus 7x, because that plus sign belongs to this entire second numerator. Okay. Now, of course, is there anything to distribute here? No, there's not. So you don't need those parentheses. I'm just being very consistent, because what if this were a subtraction sign? Would you be subtracting 7, or would you be subtracting 7 minus 7x? Right. If this were subtraction, that subtraction would belong to both things. So if you're not careful about locking up these numerators, especially if you have subtraction, it's going to change the sign. Yeah, you're going to mess up your sign, because if you are minusing a numerator, you are minusing that entire numerator. So lock it up, because if you're minusing a numerator, you're going to have to distribute that minus sign. So just be consistent and lock up your numerators. Even if it's plus, it's like, oh, that's overkill, but it doesn't hurt. Then you can say, that'll always give your brain a check. Oh, I need to distribute first because I'm adding the whole thing. Well, it's adding, so I can just drop the parentheses.
So when you add those together, are you adding the x's together and then the...
Exactly, like terms. Because this is plus, there's nothing to distribute. So I just do 8x minus 5 plus 7
x minus 7?
minus 7x, right? And that's over x squared plus 6x plus 8. Right? Because I could just drop the parentheses there. I'm just emphasizing you need the parentheses, especially in case of subtraction, so just be consistent. Lock up your numerators. So I'm ready to clean up my numerator here. My denominator I'm just bringing along for the ride. So I've got 8x minus 7x, right? You just combine like terms now. 8x and 7x are like terms. Negative 5 and 2. Now go ahead and keep that, lock that up, okay? Simplified 4 terms down to 2, just combining like terms. Okay. Well, not yet. Remember, you cannot cancel out factors of 1 until you have factors. The rule is cancel out factors of 1, so one must factor first. Now, you could have factored at the beginning, but that just kind of makes it a little messier. It's a little cleaner. I'm waiting to the end. I know I'm going to have to factor it. Now's the time to do it. Okay, it's not linear. It is, in fact, a quadratic trinomial, an a equal 1 quadratic trinomial. So you know it's going to factor into 2 binomials with x and a sign pattern of plus plus. And what are my numbers?
42.
Right. Double check. X squared, 6x, 8, check. And I have, now I can cancel out factors of 1. Keep my rational bar, what's left on top? Nothing, so I have to put a 1, right? And on the bottom I have, right, which I can leave locked up, that doesn't hurt. You know, I don't want to accidentally cancel out terms. Remember, you can only cancel out factors. And can I drop that 1? No. If it's on top, no, because the 1 over something is different than just the something. Okay? Just like 1 over 8 and 8 are totally different things. If something's on the bottom, you can't magically move it to the top. That 1 has to stay. It can't be dropped like when 1's on the bottom. Okay? Not too bad so far, right? Okay. All right. So let's shift now to looking at uncommon denominators. Our examples so far have had common denominators. The denominator is common already. It stays the same. You just want to be very careful and organized about locking everything up. Being careful of your sign here. Since I was minusing 9, that minus belongs to this entire numerator. Well, this numerator is just 9, so I don't have to worry about distributing anything. But you want to be aware that minus belongs, minus or plus, belongs to the entire second numerator. So if you've got something messier in the second numerator, make sure you lock it up, because you're going to be